Hello, this is a quick recap of the height of collimation method for leveling. I've received a number of emails from people that have problems with that part of the course, so I thought I will do a very quick screencast to explain some of the concepts and the procedure of obtaining the reduced levels and the adjustments using the height of plane of collimation method in leveling. You see here the example that you have in your notes, and we have a column of the back sides, the intermediate sides and the fore sides, and on the remark column we have the first point with a note of OBM, ordinary benchmark, and it's high above ordnance datum, so that is 4987 above ordnance datum, and then all the other points that we required on the leveling. If we finish with the last point at TBM, a transfer benchmark or temporary benchmark, which is a 4871. Now in leveling, the known points we take as given and as points that we know the reduced level of these points, of the benchmarks. So the process of the leveling is not to find the new reduced level of these points. These are the points that were used as control and they're given. The point of the leveling is to find the reduced levels of all the other points, the A, B, C, D, E in this example. The way we start is that by taking the backside, the first backside from instrument position 1, and this backside is taken on the known point at the benchmark. So basically we put the staff at this point and we measure, read, the reading is 2.191. So obviously the staff reads 2.191, and if we add to that the reduced level of the point that this reading is taking at, which is 4987, we arrive at the height of plane of collimation, which is the plane that the line of collimation prescribes when the telescope is rotated on horizontal plane. So that gives us the height of plane of collimation for the first position of the instrument. So that is 52.061, and is basically made by adding the backside 2.191 to the reduced level of the first point, which is 49870, which is basically the benchmark. Now we want to find the reduced levels of points A, B and C. What we need to do is primarily take the reading at point A from the staff 2.505, and if we remove it from the height of plane of collimation, which is now being calculated, we get the reduced level of point A, 49556. Similarly, if we get the reading at point B, 2.325, and remove it from the height of plane of collimation, 520.61, then we'll get 49736. Finally, the last measurement, the last reading from this instrument position, the instrument haven't moved yet, is 1.496. Because it's the last reading for this set of measurements, and then after that the instrument will move, it is a foresight, so it goes in the column, in the third column and foresight. Now, obviously, the reduced level of change of point C, it is the 1496 removed from 52.061, and is 50.565. This is the reduced level of point C, which is a change point as well. Now at this position we'll change the position of the instrument, we'll move it, but the staff remains at that point C. So the staff remains at the same point, and when we set the instrument again, we take our first measurement from this new instrument position, which is now in backside because it's the first measurement of the new instrument position, and is 3.019. As you see here. The problem here is obviously that the height of plane of collimation has now changed. The reason it has changed is because the instrument moved to a new position. So we need to calculate a new one. How we can do that? Very simple. We add the new measurement of backside 3.019 to the known now reduced level of point C, 50.565, and that will give us the new plane of high collimation for the new instrument position, which is 53,584. Now, having the new height of plane of collimation, we can now find the reduced level of point D by subtracting the intermediate side here for point D, 2.513, and then we get 51.0714 point D. Similarly, if we want to find point E, we subtract 2.811, which is the foreside, that means the last measurement of this instrument position, from the height of plane of collimation here, 53.584, and we get 50.775. Now we have the reduced level of point E. We'll move our instrument again for the last time, and therefore the next measurement will be a backside, will be at the same position as position E. And then if we need to get the height of plane of collimation for this position of the instrument, we add the backside to 1.752 to the reduced level of point E, 50.775, and we get 52.525. And finally, we don't have any other intermediate sides for this instrument position. We just have another side, and that's the last one, and therefore it's a foreside. Therefore, to get the reduced level of the last position, we subtract the foreside 3.824 from the height of plane collimation, and we get 48.701. Now you see that the last measurement was made over the point of a temporary benchmark. That means that the stuff was on the point of a temporary benchmark, and we use that obviously as a control because we know that the temporary benchmark is at 48.71. So we didn't really need to calculate this. We know that the temporary benchmark has this above ordinary datum height, which is 48.71. Now you see that our calculation says that this point is at 48.701. Obviously, there is an error in our calculation, as there is an error in our leveling, because we have small errors in citing the staff. The staff might be not perpendicular. It's a number of reasons that leveling is not as accurate. So what happens is that we see that we have what we call a misclosure of 9 millimeters. The measurement that we get for the benchmark is 48.701. It should have been 48.71, and we are 9 millimeters out. Now, the problem is that in leveling there is an allowable misclosure. That means that if our misclosure is less or equal to the allowable misclosure, then we can proceed to the adjustment phase. If our misclosure is a lot higher or higher than the allowable misclosure, we have to redo the leveling in order to get our misclosure within acceptable limits. So assume here that the misclosure is acceptable, and the way we can assume that is by calculating how much is the acceptable misclosure, which is plus or minus 5 times the square root of n, where n is the number of instrument positions. So n here is 3, square root of 3 times 5, it is about 9 millimeters. Obviously, if something is less than a millimeter, we'll round it up to the closest millimeter. So we have our misclosure to be acceptable here, the 9 millimeters. Now, how we go and proceed to adjust this? The adjustment is given at a different slide, so I'll go quickly through the checks. You have all this at your lecture material. So here is the plus or minus 5 square root of n, the allowable misclosure. So we are within the allowable misclosure for this example. And here we see the corrections. Now the adjustments are very simple. We don't adjust less than millimeters, and we never adjust the benchmark. The reduced level of the ordinary benchmark is 49,870. We don't really need to adjust this because we know what it is, so we leave that empty. Now basically what we do, we are proportion the required adjustment equally to every instrument position. Now we're lucky here because we have 3 instrument positions and 9 millimeters to a proportion. That means that every instrument position gets 3 millimeters of correction. In case that we have 4 instrument positions and 9 millimeters, then one instrument position will arbitrarily be chosen to have a different correction than the rest. So we might have 3, 3 and 2 and 1, or another kind of arrangement. So we don't really do corrections of less than a millimeter. So we cannot, if we have if the allowable if the misclosure is not really divided clearly by the number of positions, then we don't really adjust by less than a millimeter. So what you see here, the first instrument position gets 3 millimeters. The first 3 measurements gets 3 millimeters. The next instrument position will get 6 millimeters, and that is the 3 millimeters which are allocated as a correction for this instrument position, plus the 3 millimeters that is already carried in the system. Okay? And then the final instrument position gets 9 millimeters, which is the 6 millimeters already there, plus the 3 millimeters for this only, which are allocated only for this instrument position as a correction. So finally it gets the full 9 millimeters, and when we adjust the last reduced level here, we get to the 48710, which is basically what the dBm should have been. So all our measurements are adjusted, and we can proceed to use these adjusted reduced levels on any other calculations. Okay, so I hope this makes some sense, and good luck to your exam.